Welcome. Today we will discuss two and multi-way ANOVA. I hope that you have understood one-way ANOVA. So, I also equally hope that you will be able to work with two and multi-way ANOVA. This way, one way means one factor, two way means two factor, multi-way means three or more factor. So, what is that two way? If you consider radar scope example, so the response variable y, that is the intensity level at detection, detection of targets. And if you recall, we say that one factor A is ground clutter with three levels: low, medium and high, and type of filter B, with two levels, type 1, filter type 1 and filter type 2. So, what I can say that if you do a random experiment, actually you are having a situation like this. This side A, ground clutter, this side B, type of filter. So, you have three levels of for ground clutter: level low, I can say 1, medium maybe 2 and high 3, and you have two levels. So, type 1 filter and another one is type 2 filter. So, this is level 1, this is level 2. So, you have how many experimental settings? You have 6 number of experimental settings or treatment combinations. This is one, this one is another one, this one another one, another one, another one, another one. So, here low and type 1, here medium in type 1, medium type 1, like this. What does it mean? You are conducting an experiment in such a manner that suppose A factor level 1, then B factor level 1, then you are getting y value, here the intensity level at. So, intensity level at, so this is maybe y 11. If I go for, so again this is 1, this may be 2, and this is 2, 1, 2, 2, 3, 1, 3, 2. So, you will be getting several. So, what happened here? This means y A1, B1, 1, 1, 1, 2, 2, 1, 2, 2. So, like this. But when we I will show you the data, I will not represent in this manner. There will be replication. One more things will, one more direction will come. So, anyhow, okay. So, then in this case, this is a two factor experiment. two factor experiment. Now, if you want to develop a ANOVA model for this, it will be a two factor ANOVA model, and when you analyze the data, you have to analyze considering that two factor and their interactions are there. Okay. So, what does it mean? The y, here the response values, y values, here also y values will be there. All those response values not only depends on the ground clutter, it also depend on the, it may depend on the type of filter. In addition, it may depend on the interaction between ground clutter and type of filter, that is interaction between A and B. So, effectively sources of variation will be not only A, it will be B and their interaction A B, and plus there will be random source, that is error. So, accordingly the observations will be partitioned reference to A factor with reference to B factor with reference to their interactions, and obviously error will be there. Okay. So, this kind of data will be analyzed using 2OA ANOVA. Okay. So, we will come to some other example, but for the time being you please understand 2OA mean there are two factors and each of the factors has at least two or more labels. So, that means there will be at least in A label for A factor, B label for B factor, and there will be A into B, A B treatment combinations, and in each combination there will be n number of experiment. Obviously, in the random order it will be done. So, in total you will be having A B into n number of experimental runs, or the observed data will be A B n. Okay. So, let us see what will be the model for 2OA ANOVA. You see the basic two factor model. So, here again what I will do, we will see the table first. Now, see this table, factor A, factor B, A has A number of labels, B has B number of labels, and each cell here in this table is a treatment combination. So, A at level 1, B at level 1, this treatment combination. Similarly, A at 1, B at 2, so there will be A B treatment combination, unique independent treatment combinations. And another one interesting one is that in each of the combination you find out that there are n number of experimental runs, n number of data available. So, as a result we index this data like this y, I, j, k. So, I stands for that 1 to A, that means this is the treatment level for factor A. J stands for 1 to B, treatment levels for factor B. K is replications. So, it will be 1 to n number of replications will be there. So, this is the general data, and our table is like this 1 2 like dot 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 A, and here 1 2 dot 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 B. And here y 1 1, as I told you, I shown you earlier also that y 1 1, but at y that 1 1 level there will be n number of there will be n number of experimental runs. So y111, y112 like this, y11n. So in general yij1, yij2, so like this yijk, yijn. So there will be this general observation yijk. You can partition this yijk equal to grand mean mu, okay, plus that is A factor effect, B factor effect also. So tau I is the factor A treatment AF effect, beta j for B treatment effect, plus tau beta ij, that is the interaction effect, plus epsilon ijk, epsilon ijk. So this is my ANOVA model. So you understand now, I from 1 to A, j from 1 to B, k from 1 to n, and this is your model. So I can say other way also, this is row effect from considering this kind of table, this is column effect. So other way, row treatment effect, column treatment effect, that is interaction effect, this is error, and this is grand mean. Okay. So now you may be interested to add this together. So you can write this one equal to mu plus mu ij plus epsilon ijk, mu plus mu ij. So this mu ij is row, column and treatment, this all those things. So mu ij here, mu ij every cell, this mu ij every cell, there will be a mean value. So the yijk, so the general value will be grand mean plus mean of this plus error of this. So where mu ij equal to tau I plus beta j plus tau beta ij, yes, tau beta ij. Okay. So let us see in the table again. Now there will be, if you take sum total across rows, that will be I dot dot, this one. If you take sum total across columns, that will be y dot j dot. If you take sum total of observation in a cell, it is yij dot. If you tell all the grand total considering A, B, N, this is the case. Okay. And you can calculate average also. If you compute average of across rows, then the row basically you see there are B number of columns, and under every cell there is n number of data points. So that's why it will be divided by Bn. For column average, the column total will be divided by An. For cell average, the cell total will be divided by cell number n, and for overall average, the overall total will be divided by total number of observations. Okay. In this case also there will be random fixed effect models and random effect models. We are considering fixed effect model, and please keep in mind that we are basically interested to know whether the row treatment and column treatment effects present and their interaction effect is there or not. So that means we want to know whether the factor A affecting the response variable, factor B affecting the response variable, and their interaction also playing a role in the observed response values. So, that will be tested. So, as a result here there will be three different null hypotheses, and we will be testing it. Now, the test will be done using analysis of variance. So, the similar type of calculation we will be doing. First, partitioning the general observations into overall average, into row average, into column average, and into cell average plus errors, and then making their sum square total as the treatment, row treatment sum square, column treatment sum square, then interaction sum square, and error sum square. Okay. So, this is what we will be doing. In one way ANOVA, the sources of variability are the factor itself and the error. In two-way ANOVA, sources of variability are factor A, factor B, their interaction, and error. 4 sources will be there. Okay. Now, see the partitioning. As I told you, okay, let me what is the general yijk, that is the general observation. Okay. So, this can be written like this y dot 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 bar, this is the grand average. So, you can write now yi dot dot bar, what is this? This is row average. I can subtract this using this one grand average also, plus I will go to dot j dot bar minus y bar dot dot dot. So, this is my column average. Other way you can say row means factor A average, factor B level average. Okay. So, plus if you see that here what happened, this is one time plus minus this, but this 2 time you have already taken. So, if I write like this y I dot dot bar plus y dot j dot bar, then I write this one minus this because this is for plus consider plus y dot 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 this. Okay. So, this and I add one more term here y I j dot, this is my cell average, this is my cell average. Then what is left here? This one will be cancelled out by this one. This will be cancelled out by this one. yi dot dot this will be cancelled out by this one. Y this will be cancelled out by this one. Then this will be cancelled out by this one. So, the remaining this also to be cancelled out. So, if I write y I j k minus y I j dot bar, then this will be cancelled out by this, then y I j k equal to y I j k. So, essentially what you have done, then you have written a general observation in this way I j k minus I dot 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 bar, this is the deviation, individual observation deviation from the grand mean. I can write this equal to I dot dot bar minus I triple dot bar plus y dot j dot bar minus triple dot bar, okay, plus I can write y I j dot bar minus y I dot bar minus y dot j dot bar plus y I triple dot bar, then plus I can write y I j k minus y I j dot bar. So, this is the general deviation for individual observation. This is the deviation of the row average from grand average. This is the deviation from column average from the grand average, and this is the basically the deviation in the cell from cell average to the grand average and other things, because combiningly, and this is what is the deviation from every observation to its cell average. This is the partition. Now, what you can do, you can square it, then take sum, triple sum will be there, here also triple sum, and you will ultimately get this kind of results. So, let us see the slide here. In the slide itself, that means the left hand side, you see the left hand side, that is the individual observation is subtracted by the grand average, and when we take the square, and this is known as sum square total. And this quantity, when you expand it and then take the appropriate sums, you will find out the sum of the cross term products will be vanished. So, what will remain here will only, it will remain only this Bn into this, An into this, N into this and this. So, this if you carefully look the first one, you see that it is basically talking about the difference row level row difference average from the grand average, here column average from the grand average, here cell average from the rest, and here basically the individual observation from the cell average. So, this term is known as the row effect, row sum square row or sum square A, this is sum square B, this one is sum square AB, and this one is sum square SE. So, the the variation part, which is basically sum square total is now partitioned into sum square factor A, sum square B, sum square AB and sum square A. Like in one way ANOVA, you have seen SST equal to SSA plus SSE. Here two more terms coming, because the B source of interaction and your B source and interaction source are coming. Okay. So, here what happened ultimately, you will find out that in the earlier case like this, that when we talk about the one way ANOVA, we say that this what is n here, total number of observation here will be A B into n. So, the degree of freedom here will be n minus 1, and this will be A minus 1, this will be B minus 1, plus this will be A minus 1 into B minus 1, and this last one will be your AB into n minus 1. So, the degree of freedom is also partitioned, and if you add all those things, this is nothing but AB n minus 1, because n equal to AB n. So, other way this can be written like AB n minus 1. Okay. From here you can develop the ANOVA table. See the table here. So, if you see the table, sources of variation, A treatment, B treatment, interaction, error, SSA, SSB, SSAB, SSE, SST, these are the degrees of freedom. Compute MSA, MSB, MSAB, MSE, and then what is this? The SSA by their respective degree of freedom. So, what you want to test, whether A treatment effect is there or not, you create a statistics value for A, that is MSA by MSE. Similarly, you want to test whether B treatment effects are there or not. So, compute F0 for B, MSB by MSE. Similarly, you want to know whether interaction effects are there or not. So, compute F0 for MSAB by MSE. So, then all those things will be tested using appropriate F statistics. So, what will be the degree of freedom for this F0, first F0, that F statistics? There will be numerator A minus 1, and denominator AB into n minus 1. The second one B minus 1 AB into n minus 1. Third one A minus 1 B minus 1 into AB into n minus 1, that way. Okay. So, what are the hypotheses? You see the hypothesis. Hypothesis testing for equality of row treatment effects, that means all treatment are equal here and at least one treatment. Okay. So, you just write down this one, that tau I equal to 0, and this is basically mu 1 equal to mu related to mu 1 to mu A. This is similarly beta j equal to 0, at least one of the beta j not equal to 0, and this one is like this. So, I am writing this one carefully. What happened here? When I am talking about A treatment, so I have mu 1 to mu 2 to mu A levels, or H0 I am creating like this, tau I equal to 0, H1 tau I not equal to 0, or other way mu 1 equal to mu 2, like the other one. Okay. Similarly, for beta B you are creating that beta j equal to 0, beta j not equal to 0. Similarly, for AB, what your H0, this is H0 and H1, and this H0 is tau beta ij equal to 0, and H1 tau beta ij not equal to 0. Obviously, for this and this case, at least one of the treatment or interaction is not 0. That is what is the test. So, now you see the computation part. You calculate how do you compute manually, or it is easy computation for equal sample size. SST, a sum total of all the observation squares minus grand total square by ABN. For SSA, sum total of row total squares divided by BN, and in my end to the correction factor will be subtracted. Similarly, SSB. Now, another concept here is SSB, SS subtotals. SS subtotal means the cell K, for every cell we are interested in. In the cell means the every observation is Yij and K is changing. So, K is 1 to n, not K is. Now, if you make for every cell the total, then this is basically Ij dot, that square when you sum up across all the cells, you will be getting this quantity, and it will be divided by n and subtracted by the subtraction factor, you will get subtotal. Then what is SSAB? SSAB is subtotal minus SSA, SSB, something like this. Okay. So, let me repeat the calculation. The calculation is SS total equal to 3 sums I equal to, suppose you write I equal to 1 to A, j equal to 1 to B, k equal to 1 to n, then y I j k square. You have seen this one, minus this is the total square, grand total square by n, n equal to a b n. Okay. Suppose you want to know SSA, what you require? You require I equal to 1 to A, then y I dot dot square minus y dot 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 square by A B n, but here you have to divide it by 1 by B n. Similarly, SSB you will find out 1 by A n, j equal to 1 to B, y dot j dot square minus y dot 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 square by A B n. Everywhere you see y grand total square by A B n is subtracted. Then you are creating SS subtotal, which is basically 1 by n sum total y I j dot square k equal to 1 to n minus y dot 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 square by a b n. Then you are finding out a interaction which is SS subtotal minus SSA minus SSB. Then you find out SSE which is SST minus SSA minus SSB minus SSAB. This is the computation part for sum squares, and this will be used in ANOVA table. Now see the table: SSA, SSB, SSAB, SSE, SST, all those the computation I have shown, and now you will be able to find out this. Okay. So let us see one example. Now example is this. Now what happened? We introduced that filter type. Please remember, I told in the beginning that this this experimental data is taken from one of the example of Montgomery's book, and here what happened, not only this ground clutter and filter type, but there is another one, operators, different kind of operators. So it is a two factor with blocking that experiment was done, and the same data is taken. And I first what happened, we ignored the filter types and operator in one way ANOVA case, and we found there is no effect. Now when two-way effect is coming, that operator effect is ignored, and we are assuming that this type of data we will get even if operator effect we will not consider. So as a result, this is the type 1 and type 2 filter type, this 12 data points and here 12 data points for different ground clutter level. And what we have done, basically we have computed all SST, SS clutter, SS filter type, SS interactions using the formula I have already given to you. What are the formula? Let us see this formula. These are the formulas. So what I have done, these are the SST, SSA, SSB, SS subtotal, AB, SE, these are the formula. Using this formula, you have found out SST for that example, and similarly up to SSE. Come to the slides now. What happened? SST value is 1985 point this, SS clutter value is this, SS filter type is this, like this, and then using ANOVA we found out the F0 value is 5.18, 27 in this. Now you know that this 5.18 value is little higher value. Now when we compare with the tabulated value, considering the respective degrees of freedom 2 and 18, and that value is less than this for alpha equal to 0.05, and obviously then the 1 and 18 also less than this 27.5. So filter clutter type and filter type becomes significant. So that means there is difference in the response value, variable value, which is here in that is the intensity level at the time of detection, that differ if the ground clutter level changes from the low to medium to high. We do not know whether it is low to medium, low medium where it is different, but there is at least if you change from low to medium or low to high or medium to high, in one of the case there will be a difference. That is also true for filter type. That means if you use filter type 1, the intensity at level at target detection will be different if you use filter type 2. But in one factor case, when we have considered the same data with only ground clutter, and as if there is no other factors affecting, and the data what we have got actually same if we do that one factor level experiment, then we have analyzed and we found that there is not significant difference for different ground clutter level. When we introduce the type 1 and type 2, that factor that filter type, there is a difference. So this is the beauty of introducing more factors. Okay. And another interesting thing is that the interaction between the ground clutter and filter type is insignificant. Okay, there is no significant means there is no dependency between these two factors. So, fantastic. So, we just we what we have discussed then in this lecture. In this lecture, we have I conclude the 2OA ANOVA part now, that in 2OA ANOVA there will be two factors. There will be factor A with 1 to A label, factor B 1 to B label, and the model will have tau I, that is for factor A. There will be the treatment tau beta j, that will be for factor B, and there will be their interaction tau beta I j, and obviously there will be error epsilon I j k. Okay, so there are how many sources of variability? Sources of variability A, B, interaction and error, and finally total. This is basically sources of variability. Then we have computed SS. So, that is for total it is SST, for error it is SSE, for interaction is SSEB, for factor B and for factor A, like this. Then you computed degree of freedom, it is A minus 1 for A, B minus 1 for B, A minus 1 into B minus 1 for AB, then your AB into N minus 1 for error, and AB N minus 1 for total. Then what you have done? You have computed MS. MS is nothing but SSA by A minus 1, this is for MSA. Similarly, MSB will be SSB by B minus 1. So, MSB, that means SS by its by its degree of freedom, and similarly you will calculate MSAB, you will calculate MSE, you do not require to there is nothing not required for other things. Okay. So, then you create an F statistics or F0, that means when hypothesis is true, then this is nothing but MS for treatment A it is MSA by MSE, for treatment B it is MSB by MSE, for treatment AB it is MSAB by MSE, and what you are doing, you are testing hypothesis like this H0, in this case that tau I equal to 0 versus tau I H1 tau I not equal to 0 for at least 1 I. Similarly, here H0 beta j equal to 0 versus beta j not equal to 0 for 1, like this. And similarly your AB also interaction. Then what happened? There will be your threshold value, which is F alpha, numerator degree of freedom and denominator degree of freedom. For the first case, factor A case, this one is A minus, nu 1 is A minus 1, and nu 2 will be always same, because this is the error degree of freedom. So, this is AB into N minus 1. So, now if any of the computed statistics F0 value is greater than this value F alpha, this usually alpha we consider as 0.05, then if this is the case, then that corresponding treatment effect is there or interaction effect is there. If this is less than this, the effect is not there. And with an example we have shown, the radar scope example, we have shown that the ground clutter and filter type effect is there, but interaction effect is not there. So, thank you very much for your patient hearing. Thanks a lot.